discuss about the rules regarding chemical reactions, chemical equations. Okay, this is only for class 10 students. How you are going to write the chemical equation, what is the importance of chemical equations, that we are going to discuss, right? So this topic mainly covers inorganic portions, inorganic chemistry. That means the compounds, the acid, bases, salts, okay, excluding organic chemistry, okay. Now the first, this is the rule for chemical equation. Here we are going to discuss the example, okay, and here we are going to highlight the importance, okay, how that particular equation is important. Where do you find, where you have come across this chemical equations? This is more important to understand, okay. First, let us consider an active metal. An active metal reacting with water, okay, it forms metal hydroxide, displacing hydrogen, okay. Now what are active metals? The metals which are most reactive. Let's take the example of sodium, potassium, calcium, PSC, okay. So under this we can give an example that if sodium reacts with water, it forms sodium hydroxide, liberating hydrogen, right? And what is the importance of this equation? Okay. Now, when you prepare the bases, this is the base, metal hydroxide. So this finds application in preparation of bases, okay, rather soluble bases, because these soluble bases are called alkalis. This is an alkali, okay. The second, if you burn a metal or react a metal with oxygen gas, okay, you get a metal oxide, right? Now, example for this particular reaction, let us consider magnesium burning in oxygen, it forms magnesium oxide, okay. Now in this reaction you see magnesium oxide, this is a base. So again we can use this reaction when you want to write the preparation of a base using a metal, right? Third, if you consider a non-metal burning in oxygen, okay, it forms a non-metallic oxide, okay. This is also called acidic oxide, okay. And this metallic oxide, this is also called basic oxide or simply a base, okay. Now let us give an example. If you burn carbon in oxygen, you get carbon dioxide, okay. Now this is an acidic oxide. So if you want to prepare an acidic oxide, preparation of acidic oxides, okay, which are also called non-metallic oxides. You know why they are called acidic oxides? Because these acidic oxides dissolve in water to form corresponding acids. Let us give one example. Now what happens when non-metallic oxide dissolves in water or reacts with water, okay, then it forms the corresponding acid, okay. Now let us give an example over here. Take the example of CO2 dissolving in water, it forms carbonic acid, okay. Now you know that this is an acid and this is an acidic oxide. So acidic oxides are those which dissolve in water to form the corresponding acids. What is the importance of this reaction? This can be used for preparation of acids, right? These are the acids. You can use sulfur dioxide plus water, sulfurous acid, sulfur trioxide plus water, sulfuric acid. In this way, there are several acids which can be prepared. All these topics are coming in the chapters which you have come across, okay. Fifth, metallic oxide. This metal oxide, okay, metallic oxide, if you dissolve it in water, it will form alkali, okay. Why I am telling dissolving water? Because you know only those bases which are soluble, they dissolve in water to form alkali. Now let's take an example over here. If you consider sodium oxide, this is a soluble base. It dissolves in water to form alkali, that is NaOH, okay. So this is how the reaction goes. So we can write, this is used for preparation of bases that is soluble, okay. As you come across in acid basis salts, in the preparation of bases you can give this particular equation as an example, right? Now sixth, what happens when a metallic carbonate is heated, okay. We get a metal oxide plus carbon dioxide gas, okay. Now for example, if you heat calcium carbonate, it forms calcium oxide plus carbon dioxide, okay. Now this reaction, the importance of this reaction could be analyzed with this fact that you can prepare a base from a carbonate. So it is the preparation of a base, okay, using a salt. That means this was the preparation of a base from a metal oxide, okay. This is the preparation of a base from a metal. This is the preparation of a base from a salt. So this is the importance, preparation of a base using a salt. So there are some questions given in which this could be the headlines. Then you forget about where you have come across this. This is the reaction, okay, and this is the rule. Seventh, if you heat a metallic nitrate, a heavy metal nitrate, okay, this is the notation for decomposition brought by heat, okay, then you get metal oxide plus a reddish brown gas NO2 plus a colorless gas O2, okay. Let us give an example. If you take copper nitrate and heat it, you get copper oxide plus nitrogen dioxide, that is the reddish brown fumes, plus colorless gas oxygen. Now the importance of this reaction is that you are preparing again a base using a salt. So this is one significance, preparation of a base using a salt. The salt could be carbonate or a nitrate. Now that depends upon the question given, okay. Next, if you make a metallic carbonate react with an acid, okay, it forms salt plus water plus carbon dioxide, right? You know what is the difference? What is the difference between metallic carbonate reacting with an acid, okay, and a metallic sulfide reacting with an acid? Here we are going to discuss. So first and important thing, if you make a metallic carbonate react with an acid, it forms salt, water, carbon dioxide. Look at the importance. The evolution of this carbon dioxide gas with effervescence, okay, indicates the presence of carbonate ion, okay. Carbonate ion means CO3 minus 2, okay. This is the test for anions given in salt analysis, okay. So simply the evolution of carbon dioxide confirms the presence of carbonate in the salt, okay. Now let me discuss one equation. Calcium carbonate reacting with dilute acid, it forms calcium chloride plus water plus carbon dioxide, right? So what is the importance of this reaction? This reaction proves the presence of carbonate radical in the salt, okay. The presence of carbon dioxide, the evolution of carbon dioxide confirms that the anion present is this one, carbonate, and you can test this carbon dioxide, pass it through lime water, it turns milky, it is odorless, having no odor, and when you pass through KMnO4, pink solution doesn't change. That confirms it is CO2 definitely, but not SO2, because SO2 also turns lime water milky. Next, if you react a metallic sulfite plus acid, it forms salt plus water plus SO2, okay. The evolution of SO2 can be tested by the action of KMnO4 that turns pink to colorless, and it also turns potassium dichromate solution orange to green. What more thing it confirms? The confirmation is proving that this sulfur dioxide tests the presence of sulfite in this radical, okay. Sulfite means SO3 minus 2, okay. So let us give an example over here. If sodium sulfite reacts with HCl, it forms sodium chloride plus water plus sulfur dioxide, okay. So whenever you react a metallic sulfide with acid, it forms salt plus water plus SO2. You know, sulfur dioxide has pungent odor, it turns KMnO4 solution pink to colorless, and it turns potassium dichromate solution orange to green. All this confirms that the gas is SO2. So here the evolution of SO2 confirms the presence of sulfite in the salt. What more thing? There are some questions which are asked. Differentiate between sodium carbonate and sodium sulfite, okay. So you don't get any difference in the textbook. You have to give a chemical test to differentiate between the two salts. So the chemical test is add HCl to both of them, that means plus HCl, this will give you CO2 gas, and plus HCl, this will give you SO2 gas, right? So this is how you can differentiate between the two salts. So there might be questions based on chemical properties. So the rules, the properties of chemical reactions are very important, And you know, this is the backbone of chemistry. Without equation, chemistry is history. Now 10th, we are discussing a reaction in which metal sulfide reacts with acid. It forms salt plus H2S. H2S means hydrogen sulfide. The most characteristic odor, a gas with a rotten smell. So the evolution of sulfide, H2S, this gas evolved confirms the presence of sulfide in this radical. Sulfide means S minus 2, right? So let's give an equation. If you make FeS iron sulfide react with HCl acid, it forms FeCl2 plus H2S. Okay? So this proves the presence of sulfide S minus 2 in the radical. See, these are very important because in salt analysis, when you are going to discuss about the cation, anion present in the salt, then these gases confirm the presence of negative ions, that is acid radicals, right? Now, next rule we are discussing, you take any metal chloride, react it with concentrated H2SO4. Okay, this forms the salt plus HCl gas, right? You know what is the test for HCl gas? It is the gas that turns blue litmus red, and it is the gas when passed through silver nitrate forms a curdy white precipitate of silver chloride. Then if you dip a glass rod in ammonium hydroxide, bring it near, it forms dense white fumes. All this confirms that the gas is HCl, and the evolution of HCl confirms the presence of chloride, that is Cl minus, in the salt. So here we are taking an example. Suppose you take sodium chloride, make it react with concentrated sulfuric acid. This is concentrated, okay, and we are considering temperature less than 200 degrees Celsius. It forms NaHSO4 plus HCl. Okay. Now the importance of this reaction is that, first of all, it proves the presence of chloride in the salt. Okay. This also proves the dibasic nature of sulfuric acid, because sulfuric acid can form two series of salts. One is sulfates and the other is bisulfates. This is the acid salt. Now what happens if the temperature is more than 200 degrees Celsius? Okay, then it forms a normal salt, Na2SO4 plus HCl, right? So this equation simply tells us, the two equations, that sulfuric acid can form two series of salts. One is sulfates, that is normal salt. The other is bisulfate, that is acid salt. So a salt of normal nature and acidic nature are formed. Therefore this confirms that sulfuric acid is a dibasic acid. What more? This equation also confirms the presence of chloride in the salt. Third, this equation also proves the non-volatile nature of sulfuric acid. That means sulfuric acid has a high boiling point, about 338 degrees Celsius. So those acids which have high boiling point are called non-volatile. So this equation also proves the non-volatile nature. Proves dibasic nature, non-volatile nature, okay, of H2SO4, and this also can be supported for preparation of HCl gas in lab. So many outcomes are there. If you go through these equations, they help you a lot. Those are the questions which could be asked, and this is the solution. Okay. Next rule, if you consider a metal nitrate, make it react with conc H2SO4, you get a salt along with HNO3, nitric acid. Okay. For example, if you take sodium nitrate, react it with conc sulfuric acid, okay, and same condition as the first, less than 200 degrees Celsius, it forms an acid salt NaHSO4 forming HNO3. Now this equation again supports the non-volatile nature of conc sulfuric acid, plus it also supports the dibasic nature, because if you make the reaction possible, more than 200 degrees Celsius, it forms a normal salt Na2SO4 plus HNO3. Okay, so this proves this is the same. Okay, proves the dibasic nature of non-volatile nature of H2SO4 and the preparation of, okay, preparation of HNO3 in the lab. Okay, so this is the importance, because you feel that the chemical reactions are very difficult. No, if you go through these rules, so many questions can be linked up. Okay. The same part. Suppose we react a metal above hydrogen means above hydrogen activity series with a dilute acid. Suppose we take option HCl or H2SO4. Okay, then we get the salt along with hydrogen gas, right? See, this is a very important equation. If you select two acids and 8 metals, PSC metal, potassium, sodium, calcium, magnesium, aluminum, zinc, iron, lead, 8 into 2, 16 equations can be possibly written. See, I am writing one equation. This is the rule. This is the example. I am taking a metal above hydrogen, for example zinc, making it react with sulfuric acid. We get the salt zinc sulfate plus hydrogen gas, right? Now, the importance of this reaction is that we can prove the position of the metal above hydrogen in the activity series, right? If you want to prove that zinc lies above hydrogen, you can support this equation. Okay, this equation also confirms the chemical property of dilute sulfuric acid. This is the reaction for only dilute acids, not concentrated. Okay, because if you take the metal, any metal above hydrogen, doesn't matter, make it react with conc H2SO4, then it will form salt plus water plus SO2 gas. Look at the difference. Just by changing the concentration of the acid from dilute to concentrated, the equation is totally different. Now when you react this with concentrated sulfuric acid, okay, it forms salt, zinc sulfate plus water plus SO2. Okay. Now what is the importance of this reaction? The importance is very important because you have to compare these acids. Suppose you want to compare dilute acid H2SO4 with conc H2SO4. So this is the importance. Comparison of dilute H2SO4 and conc H2SO4, right? Now let us consider one more rule. If you take any metallic salt, okay, reacted with alkali, okay, suppose we take NaOH or NH4H also, okay, then we get a metallic hydroxide, okay, which is of course insoluble, plus metallic salt, okay. Now this single equation sums up the whole chapter of qualitative analysis, which is based on double decomposition, okay. Now what is double decomposition reaction? Suppose if AB is a salt, it reacts with a compound CD, okay, then the ions get interchanged. D comes in place of B, B comes in place of D. Look at the change, okay. Here we are giving this equation as a reference because the entire reactions of analytical chemistry based on this particular double decomposition. Now look at the example. Suppose you take copper sulfate reacted with NaOH, okay, it forms a blue PPT, a light blue PPT of copper hydroxide along with Na2SO4. So you see the ions have got exchanged, OH coming in place of this, sulfate going in place of this. So what is the importance of this reaction? It proves the test for cation. Cation means positive radical, cation copper ion, okay, because this light blue PPT is only for copper hydroxide. So the equation is based on double decomposition and the equation is for a metallic salt versus an alkali. The alkali we have selected is NaOH. If you select NH4OH also, the salt will be ammonium sulfate. Rest all thing will remain the same. So based on this you can write at least 14 equations, okay, or more. For example, let us take the salt zinc sulfate, lead nitrate, okay, ferrous sulfate, ferric chloride and compare with NaOH, NH4H. At least 10 equations you can give based on the same pattern, okay. So if you take iron salt ferrous, the PPT will be dirty green PPT, that will prove the presence of ferrous. If you take ferric, the PPT will be reddish brown, proving the presence of ferric in this way. So a single equation sums up the whole chapter qualitative analysis. The chapter is basically test for cations, okay. Next, if you take a ammonium salt, okay, make it react with an alkali, it will form a salt forming water, liberating ammonia gas. See, ammonia is a gas, ammonium is the salt, okay. You know, This is the only gas that turns litmus moist red to blue. This is the gas that forms dense fried fumes when a glass rod dipped in hydrochloric acid is brought near this. Okay? And even this gas turns Nessler's reagent, potassium mercury hydrate, brown. So when you confirm these tests, it confirms the evolution of ammonia gas confirms the presence of ammonium. This is the cation. Okay, this is the test for ammonium salts. Any ammonium salt, ammonium chloride, ammonium sulfate, ammonium phosphate, ammonium carbonate, all salts are soluble. Make it react with alkalis. These alkalis could be sodium hydroxide, potassium hydroxide, okay, calcium hydroxide, and you will get ammonia. Let's give an example for this rule, okay. If you consider ammonium chloride, which is also called sal ammonic, make it react with calcium hydroxide, that is slaked lime, okay, you get a salt, this one, calcium chloride, along with water, liberating ammonia, right? Perhaps this is the lab preparation. If you remember, this is the lab preparation of ammonia gas. Okay. What more? It confirms the test for ammonium radical. Okay. Clear? Now we have discussed this chemical equation in the lab preparation of ammonia, right? So if the question is asked on that, you can give this equation. This equation also justifies the presence of ammonium radical. Okay? There is no more test for the presence of ammonium radical in the salt. Okay? So any ammonium salt reacts with alkali to form salt plus water plus ammonia. So this is the importance. Okay? Next, if you take a metal, see, when we are discussing metal, we are not highlighting this particular property. The metal could be above hydrogen, below hydrogen, right? If you take any metal, zinc or copper, one above, one below hydrogen. If you make a metal react with dilute nitric acid, okay, this will form salt plus water plus nitric oxide, right? This is the gas evolved. This gas has no color. But supposing you are preparing this gas using these reactants, then the test tube in which you are preparing, just above the mouth of the test tube, this gas comes in combination with oxygen of the air and turns reddish brown, like this. NO plus O2 gives NO2. Okay? So the questions are asked, name a colorless gas that becomes reddish brown in contact with air. This is the equation going on. Now let us give an example. If you take zinc metal, make it react with dilute HNO3, this will form zinc nitrate plus water plus NO. Okay? See, I am not balancing the equations. That is very easy. It's based on class 7 concepts. So these are the products. Okay? So this is the test for dilute HNO3. Okay? What about if it is concentrated? If you react the same metal with concentrated HNO3, it will form salt plus water plus NO2. Look at the difference. Okay? There is a slight difference. The salt and water products are same, but the gas one involved is nitric oxide, a colorless gas, and this is nitrogen dioxide, which is reddish brown fumes. So suppose you want to differentiate between dilute HNO3, conc HNO3, then you can give these reactions. Okay? So zinc reacting with HNO3 concentrated gives zinc nitrate plus water plus NO2. Okay. So this was dilute, this was formed. So importance is that this is the test for conc HNO3, right? Now you can differentiate between dilute HNO3, conc HNO3 by giving this test. Okay, the one that devolves colorless gas that turns reddish brown above the mouth of test tube was HNO3 dilute. The one that devolves reddish brown gas right from the bottom of the test tube was conc HNO3. So this is the comparison. Clear? I hope these chemical equations will help you a lot. Okay, so you can sum up the reactions. Suppose you react or heat a metal hydroxide. Okay, you get a metal oxide plus water. For example, if you heat copper hydroxide, you will get black copper oxide plus water. The importance of this reaction is that you can use this as preparation of a base. Okay, from a base. The question sounds a little bit silly. How come you are preparing a base from a base? Well, this is a metal hydroxide. You know, bases are oxides or hydroxides of metals. So this is a metal hydroxide. Upon heating it comes metal oxide plus water. Okay, so there are some equations which might make you feel puzzled for a moment, but since you come across these equations, you can apply this when you are solving the papers. I once again repeat, please go through the rules. This will make you clear all the inorganic portions, right?